Hey guys, what's up? Eddie Aho here with KissAnalog.com. Hey, today we're going to look at some stuff I have on the bench. I recorded it before I left. I broke up the video because I think it's going to be too long. But we're going to look at the bench, look at some waveforms, watch that current in the inductor, kind of get a feel for what it does, be it big or small, and also on how to calculate the value. Okay, so yeah, let's go over there and jump on the bench and do that. Okay, guys, this is an eval card from Texas Instruments. A little danger thing says danger hot, that heat sink. Danger high voltage. Yes, it's going to have high voltage. This is our output connector. That's going to have 390 volts on it. Okay, our input connector is up here. This is where the AC comes in, and that can be anywhere from 85 to 265 volts. So universal input goes through this EMI filter. There's a bridge rectifier right there on that heatsink, so that will come through and start to charge up this cap, and this diode will let it come through and charge up this guy. Okay, without that diode, it would only charge up this cap until the boost converter kicked on, which would then charge this up. But with that diode down there, it'll let this guy get at least half that voltage. About, let's say 120 coming in, it'll get about 180. If you had 265, it's going to be closer to your 300 something volts. So it's not boosting a lot, but it always has to boost. So it's got to be above the peak value of that 265. Okay. So it comes through the fuse, a couple Y caps, combo choke here, but it's going to go through this X cap here, combo choke, X cap, and then that bridge. There is a thermistor to slow that inrush down, because now that we put this diode over here, there's going to be some inrush to charge this bulk capacitor up on the output. Okay. And at some point, the boost converter is going to start running and start helping this come up to the full 390 volts. Okay. So this connector is for the 12 volts. That's the auxiliary voltage input. And, I'm going to show you that circuit in a minute. It runs a PWM converter and all that stuff that runs the transistors that boost. Let's see if we can show you those. You can kind of see it right there in the middle. There's a little clip holding it in, and then over on the left is the output diode. Okay, there you go. So there's little clips holding those things in, kind of a side view there. Okay, now, but we do have this auxiliary voltage that we need to run the control chip and everything to run this. Okay, so let's flip that over. There's a heat sink. Okay, on the other side, look, we got some big rubber feet. I think I put those on there to make it easier to mount. I'm not sure if they came with it or if something I added. Anyway, so there's the circuitry. You can see the trace work. The input connector right here. So here's the earth, line, neutral connections. Okay, danger, high voltage. And down here is all the control circuitry. Now see all those little test pins, those test connectors? Those are really nice that they add those on there. You can put your scope probe on them. So we're going to put one on this gate, okay? And then here's the ground. Now there's no isolation on this side. It's all tied to the same ground, right? So it's just a boost converter, no isolation. So we have this ground and gate. We're going to look at that so we can see when the gate's turning on and off. And then over here, it's called the switch, and that's the switching node, okay? So we're going to look at that, but I'll show you. And then there's more test connectors over here on the output if you wanted to hook up there. So it's nice that they add those oscilloscope test connectors. It's really nice for these eval cards. Okay, so we're not going to actually test this board right now. We're going to go over this board. I have two. So what I did is I popped the inductor off. This is a boost inductor. Popped him off. And there's a connection. This connection goes down to the board, down to that pin right there. And that is our switching node. So that's that switching node I showed you on the bottom of the board. So instead, we're going to be here. Now, the other differential probe, you can see the plus, it's going up to the gate, and here's the ground. But then on this differential, I just went to the output ground, okay? Because since it's all the same ground. Now, here, let me move this guy out of the way. So that's that differential probe. That's where the leads combine. That's really cool. This is McSig's new differential probe. And that comes up here to this guy right here. So that's the DP750. So that's pretty nice. Dash 100, okay? That's a nice differential probe. The other probe we have is this guy right here. This is another really nice one, okay? And it comes down and runs over to this little amplifier, okay? Look how small that is. Anyway, that's this one. That's what we're going to be looking at the gate, okay? So we're going to be looking at the gate with that one. And then going back up to the scope, there's a current probe, okay? That's McSig's new current probe, and that is this one right here, the CP503. So we're going to look at that, okay? And we're going to kind of compare it to the tried and true. This is a CP2100B. This is been just an amazing probe, okay? It's times 10, because I think that's plenty for what we're going to see here. So we'll just look at these two just for fun, just kind of compare the two. Now the output, the load, is 400 volts, right? Well, 390. So what we have here is a Vicor brick, okay? This is a quarter brick, what they call them, because it's quarter size. It's a quarter size of a full brick. It's a standard, thing they came up with: full brick, half brick, quarter brick. This little dude right here is 300 watts, okay? That's pretty amazing. So nominally 375 volts at the input. We're going to be close to that, but this thing, it'll go up to, I think, just over 400. 12 volts on the output, 300 watts. So I'm going to use this since I don't have a high voltage electronic load. Now I do have resistors I could use, but I just thought I'd use this just to kind of show you how another way of doing things. So we convert down to 12 volts, and then from that 12 volts, we can come up to this iTech. This is an awesome electronic load. I need to learn how to use more of the functions, but we can go to 300 watts on this. So I can get this guy not all the way up to power, but I can get it pretty far, and it'll go up to 150 volts at 30 amps. So that's pretty awesome, okay? And it's the IT8512A. So I know on the camera it looks pretty bad probably, huh? It's a nice display, believe me. Anyway, we also have the picoscope. I'm going to get my laptop, hook it up, and I might switch these probes over to the pico, just because that way I can show you the waveforms, I think, a little bit easier on the picoscope than I can on the McSig. The McSig, I can transfer this stuff via Bluetooth to my iPad, so I can do about the same thing, but I think it'll be easier to use this Pico. This is a Pico 2000 series. Pretty amazing scope, especially, I mean, yeah, just crazy good. Now, you can go to the big boy, the 5000, but, I think this 2000 is an awesome scope, and so we want to try it out. All right, guys, so we have the 12 volts coming from here. Let me show you the lab supply. Sorry, it's kind of messy over here. The WampTech. I love this power supply. It's awesome. You got 3 different memory modes, but I just set this thing up. I guess I could have stored it in one of those memory modes, and it lets me turn the output on and off right here, so that's great. I love to be able to do that way. So that WampTech, pretty amazing for how small it is and how awesome it is. Okay, now, anyway, we're going to come back over here, and I'm going to show you these big old clips. You probably saw them, right? That's the AC input. This is a power cord I made years and years ago. Anyway, we're going to come over here, and that goes right there in the front of my volt box, okay? So I can switch that around, and I can dial it up from right there, bring up the voltage nice and slow. And we keep on going by this Sugon T21 soldering station. Pretty amazing station. This is something a friend of the channel, I like to call him a friend, Joey, in Canada. He sent me this. That was very nice of him. Thank you, Joey. Really appreciate that. I've only had a couple people send me gifts, and thank you, Joey. Really appreciate that. Big thumbs up on that. So anyway, use that. So my video card maxed out, had to redo it. But anyway, just found these. They're just handy. And, I thought we'd do this test here and just to look at that inductor, okay? And by the way, I don't know if you saw these as we were breezing over them, but these are a couple inductors I brought over for that PFC design. So next video, I think in the next video on this PFC, we're going to swap out these guys and see how they work. All right. Okay, guys, so just to get going, I'm going to come over here and turn on the 12 volts, and then I'll crank that guy up nice and easy. And we're going to be monitoring the scope, okay? Hey guys, I'm here with my friend, and we hope you like this video, and give us a big old thumbs up if you do. All right, guys, got my blast shield down, my glasses on, and everything's all scope probed up. Also, I got the 12 volts on. So all I have to do is bring up the AC voltage, which I got the switch on, and we're looking at the load, what's coming out of to here. So, all right, so I can go ahead and bring it up, and then let's see what our waveform looks like. And, okay, and by the way, I got 40 watts over here on the active load. Okay, so I'm going to go ahead and freeze that. I'm going to freeze that right there. Now, okay, what I want to show you is at the top of the waveform is all the waves I've captured. And the blue one almost looks like that pulsating, DC current, okay? So it almost looks sinusoidal, right? Pulsating. So that's our current. And so we're drawing current through the whole waveform instead of just a spike right in the middle without PFC. Okay, so the yellow waveform is the output voltage. Well, it's actually the voltage at the switching node. So sometimes, so here we're going to zoom in and take a look at this, okay? Now, I'm zoomed in pretty tight. Let me zoom out just a little bit, get a couple waves here. Okay, there's a few waves. Now I'm looking right here at the bottom of the valley of the voltage, okay? So when and right there the duty cycle is like 93%. It's almost, that transistor is trying to get some current out, but there's just no voltage, so it's very little. So you can see that blue waveform is just hardly doing anything. Okay, now if I move this up the waveform, try to do it slow, you can see the current starting to get that triangle wave shape, or sawtooth, I guess. So yeah, it's starting to grow, and the duty cycle is dropping a little bit. 80, it's in the 80s now. Okay, and you see the voltage starting to square up because there's actually some voltage there. It's not down the valley. Okay, now here, I'll just run this over to where we are at the, you might be able to see the little bright line that is where the window down here on the bottom is that little bright line up on top. I got so many waveforms, it's a little bit hard to see. Okay, I'm right near, the apex or the top of the waveform. So right there, our duty cycle is about 75%. This is 40 watts, like I said, and I'm not sure where the input was. I don't think I was that high, just high enough to get it running. And so that's what it looks like. So now here, let me zoom in, because what I want to do is I want to look at one of those ramps, right? Now, when the gate, the purple waveform is up, that's the gate. So the yellow one's down. The switching node's pulled down. So I know the only voltage I have across the inductor is at the input. But I don't have a probe on that right now. So if I did, I could go, okay, I have 80 volts at the input. So I can do my equation. Because I could say the rise time, the current, I can start at the bottom and go up and get that rise time, okay? So that would be nice to do, but I don't have a scope probe there. I was looking at the switching node because it's really interesting. Now, I do have more differential probes, but you know what I can do is instead of having the differential probe from ground to switch node, now that we know what it looks like, I can put it right across the inductor and actually see what the actual voltage is across the inductor at the time of the switch. So the idea, now that we can see, you can see where the gate is, you can kind of see the charging current through the inductor. It rises up when the gate's up and the drain of the FET's down to 0. The switching node's down to 0. So just the input voltage is pushing current through the inductor, it's charging it up. Then the transistor turns off, and then the voltage pops up to about 385 volts, it says. And at that time, the current drops. It ramps down, and then it starts over again. And you can see it doesn't go to zero. It's about 1 grid off of zero. So it goes down to almost 400 milliamps. Now this is 40 watts, so almost a tenth of the max power. So let's say 10% of the max power, we're getting to the point where we're almost discontinuous, right? So that's one thing you can think about. Okay, let's say if we were at 10% power, 40 watts, 30 something watts, whatever, 50 watts if it's 500 watts. And at that point, at the top, you know, maybe, and I set this voltage to 85 volts, the minimum input. So if I do all those things, we could calculate it on paper so that we could, you know, foresee what's going to happen here, right? But I'm just kind of pointing out like how this is working. Now, if I take this up to 400 watts, or well, as high as I can go with this guy, then, which is 300 watts actually. But if I do that, we'll see that triangle wave getting higher and higher off of, it doesn't come down as close to the ground. It goes back up, okay? So, or zero current, I should call it. So anyway, right now we're about 1 grid off at zero current, and then it goes back up, which is fine. So now I can lower the load until it right hits the thing. So it's just critical conduction mode. And then if I go a little bit lower, then it'll stop, flat, go up. That's discontinuous. But so I could find that spot, and then I would know at what power level and at what input voltage that occurs at the peak of the waveform, because I'm looking at the, you know, near the peak of the waveform, right? So that would be a way to investigate this design, and we can do that. We can spend more time in the next video just really coming down with exactly how they did this one, okay? But I'm just giving you an idea on this video because it'll be long enough, just showing you, trying to get, you know, into the field of play here. So now that you've guys seen it, the next time we walk through it, I can go a little quicker. I won't have to, you know, show my whiteboard and stuff. But all right, so anyway, let's take a look at this. But what I want to do is I want to put the voltage probes right across the inductor and see what that looks like. So let's do that. Okay, so I switched the probe, you know, put the black one on the switching node. So when it goes low, we're going to say the black one is the low point, and the red one will be the high point, the input of the inductor. Okay, so let's go ahead and take that off there. We're ready to bring it back up again. Okay, it's running. And whoops, I got to bring the yellow waveform up because I forgot that we're going to be at a different part of the screen. Okay, there we are. I'm just going to go ahead and freeze that. Turn off the voltage, and oh, I got pretty close to a grid, but over on the left says 151, so I'm going to move that down to 150. It's 50 volts per, so I'm right on that grid right there. So it goes up. You can see the voltage goes positive during, you know, most of the waveform, right? The duty cycle, 84%, and then it goes below that reference point, that ground, for a smaller point. Now, all right, guys, so this brings up a very important part. So I wasn't thinking about explaining this part, but now that we see it, this is a great time. All right, guys, this is a perfect time to talk about volt seconds. It's a principle that's nice to understand, and it just came up because I was going to, you know, kind of show you what's going on, and I guess it's good just to explain this. So we're getting volt seconds in this video. Awesome. So when that voltage across the inductor, you know, when I put the black probe on the output, the switching node, so when it goes down to zero, so we're 0 volts, the red probe is showing us we're about 50 volts above, you know, that line, right? So we're plus 50 volts, and it's about 85% duty cycle almost. So I don't have the time right now. Oh yeah, I do, about 7 microseconds. But let's just say it was 10 microseconds. If it's 10 microseconds long on, you know, when the voltage is plus, then, and let's say 50 volts up, 10 microseconds times 50 would be 500 volts per microsecond, okay? So microsecond volts, however you want to say that, I guess. And then when it turns off, it has to be the same. So let's just say it was off for 1 microsecond. So it'd have to go down 500 volts to have the same volts microseconds, or microsecond volts, same, you know, volt time, okay? So the volt time is the same on both ends of the waveform. If the duty cycle is 50%, you see whatever voltage it went to on the positive side, you'd see the same amount on the negative side. It'd be 50-50. But since the duty cycle is so long, it's squished here and it's really deep here to get the same time times the volts as you get over here, okay? Does that make sense? So they call it volt. So yeah, that's just called the volt second rule. And so it's volt seconds have to equal on the positive side and on the negative side. So it's just volt seconds, okay? So that's what we're looking at here on the thing. That's very interesting. So now that we see the actual voltage and the rise time, it's easier to calculate. Here, I'll just drag the screen over so it's in the middle somewhere. I'm going to try to put the rise time on a grid. So we got 1, 2, 3, 4, 5, 6, 7. Yeah, 7.13 microseconds sounds about right. Now the current, I have 1.78. But you know what? It's seeing some of that noise stuff, so that's not quite right. So let's see if I do this again, bring up the cursors, I could go, let's say right about there's where the triangle would, the sawtooth would point out. There's distortion and stuff a lot of times at the bottom, so and even at the top. See how it's distorted? So you have to kind of visualize where, if the lines were not distorted, where they would peak out at. And I'd say maybe right about there. So it's about 1.39 amps. Okay, so we could use, so in our equation, so we could use 56 volts, okay, on the yellow. So 56 volts for 7.13 microseconds, and the current change is 1.39. Let's go ahead and use those numbers and calculate it and see what it comes to, okay? You guys do it, I'll do it, we'll come back. Okay guys, I kind of moved things a little bit. It's about 1.28 amps. I think I was being a little bit too generous, because if I'm looking at the, and even that might be too generous, because there's some noise. Yeah, I'm not really sure. I have to zoom in. I should filter that waveform a little bit better, which makes it, allows you to change the bandwidth. So I could filter that blue one to get a nice, cleaner, more average waveform. And as a matter of fact, I could even sample in the average mode and get that to average out. That would probably be better to get a more accurate measurement. But anyway, if I use, and also the voltage, same thing. If I use, like, I think 55 volts and, I don't know, 1.28 amps and 7.13 microseconds, it comes out just over 300 microhenries, right? Is that right? Anyway, I played around a little bit, and when I measured that inductor, I think that inductance measured just over, it was like 320 microhenries, something like that. Might have been 330. I forget. I measured 3 different inductors. But I remember being, here. Yeah, so when I measured that inductor, it was like 300, it was actually 305 microhenries at 100 kilohertz. So actually, man, that's really close. It looks like we got really close measurement. So that's one way to measure it, and you can kind of see how it's behaving. I hope you're getting a better idea how this PFC works. And we're going to do another video where we're going to dive a little bit deeper in this, where I'm going to try to get some really clean signals, and we're going to see what they did to see at what load level where it goes discontinuous, because that's nice to know. Let's say at minimum input voltage, 85 volts, at what load level? Now, what about nominal? So 120, when does it go discontinuous? So that has to do with how much inductance. Now, you could add more inductance so you could go lower, which might be nice. the thing with adding more inductance, you got more copper turns, right? And the core itself could become saturated. So those are the kind of things you have to think about. But if your core is big enough, which these guys over here are pretty big, and you know, a little bit higher inductance, so they might be interesting to look at. So there you go. And then also, if you're going all the way up to a higher power, instead of, you know, 300, almost 400 watts here, if we're going at 500 watts, God, it's a huge range for that inductor to have to work at. So the real high range, there's going to be very little ripple. So that's the other consideration, is you want a certain amount of ripple. Okay, you don't want to have the inductor to go so flat, you know, you don't, it's almost all DC current with very little sawtooth on the top. So there's some trade-offs there. You might choose a minimum amount of, you know, sawtooth at the top end, and then just wherever the low end falls in, it falls in. Now, depending on your use case, if you're operating mostly below nominal or average power, whatever your average power is, like let's say 500 watts, 250, is that nominal? Or is 100 watts really more nominal? So you might want to take those things into consideration when you choose that inductor value. So yeah, next video we're going to dive into this a little bit deeper and give you a better picture, give you more pictures to hopefully make it more obvious. All right, hope you liked it. 2 thumbs up to my patrons as always, and thanks for watching, and like the video if you found something useful. Okay, that really helps the YouTube thing, so appreciate it. 2 thumbs up to my members of the channel. Thank you guys, and hey, we'll see you next time. Yeah, I think I might need a big thumbs up, or I might be in trouble with my friend here. So big thumbs up, appreciated. Hope you guys liked the video. Let me know. We're going to do some more videos on this power supply design, and I hope you like it.